Could wealthier communities benefit more from these resources in terms of, say, clean water, the products that can be developed, whereas poorer communities or third world countries may struggle because the technology isn't available for them? Welcome to KU Pulse, the podcast. My name is Maggie Kinsella. I'm your host for today. I'd like to welcome our very special guest, Dr. Jorge Rodríguez. He is a professor of chemical engineering here at Khalifa University, and he's here to talk to us today about a topic that most of us don't think about, but we're certainly glad he does. Welcome, Dr. Jorge.
Thanks, Maggie. Glad to be here.
Why don't we start by just telling the audience a little bit about your background, your career, and how you kind of got to this point where you are focused on wastewater and sustainability.
Yeah, sure. Yeah, I studied in Spain. I grew up in Spain. That's where I did my degree in chemical engineering. And then I continued after some period abroad in Germany. I got interested in research and decided to continue for PhD studies. And my PhD topic was on a research group, as part of a research group on environmental biotechnology. And there is where the whole microbial wastewater treatment came into play.
Okay. I was having a conversation with my son last night, and I was telling him about our conversation today. And I asked him if he knew what wastewater was. And he said, well, yeah, Mom, it's when people aren't mindful of all the water they waste. I said, well, yeah, people should be more mindful of the water they waste, but it's not quite what we're going to be talking about today. So when we have showers, when we do a load in the dishwasher, when we wash our clothes, water that goes down our sink, it goes through the plumbing system and out to a wastewater treatment facility. And there's a typical way that gets cleaned up. So from what I know, it goes through a filter system to take out the big debris. Is that right?
Initially? Yeah, initially.
And then it goes into a submission tank where the heavy stuff kind of falls. And then the lighter stuff kind of goes to the top, like oils and things like that. Yeah, and they clean out the sand and dirt. And then it looks better, but there's still pollutants in there. So they add bacteriums, like microorganisms, into that to clean it up, to eat them away. And then they submit the water into a river or an ocean where it's clean. Is that correct?
That's actually quite right. You got it.
Good. Well, glad I got it right.
You got it right.
What's different about what you're doing? So if that's the normal process, where do you come in? At which phase?
Sure. The wastewater process, the wastewater treatment that you described is the way it's done normally in cities where they have the infrastructure to do all this. Right? Okay. And in that process, some of the steps you mentioned, they are physical. You talked about settling down, right? You talk about filters. This is physical. But there are steps of the process which deal with the removal of the pollutants that are not particles, but they are dissolved. Okay. So if they are dissolved, you cannot really separate them with a filter, right? They are chemically dissolved. So they have to be consumed. And those are normally removed by microbial activity. So bacteria are going to eat basically that sugary or leftover organic material that is in our sewage, in our waste. And then they are going to, let's say, eliminate it from the water into other maybe gases or components. And the bacteria in exchange will grow. So they get a reward for that. The advantage of this is that these bacteria are particles. So then we can separate the bacteria with the physical methods that you mentioned before. So we get the water clean and the bacteria in another sludge line. That's normally the conventional way the wastewater treatment is done.
So we're not talking today just about wastewater treatment. You're now going to tell us a little bit about how we can get additional resources from this process. Can you tell us about that?
Yeah, absolutely. So these organisms that are basically natural organisms that live around us, we can enhance them by providing them the right conditions, the right food. For example, the wastewater is the food for them. But apart from doing this job of cleaning, they can also produce certain valuable components that are interesting for us. For example, in wastewater treatment plants, when we do something what's called anaerobic digestion of this sludge that is growing, we can produce biogas. And biogas is the same component as in natural gas, so it's methane. So that can be used directly for energy source. And it's going to be a renewable energy because it comes from carbon that comes from organic material, human waste, so it's not fossil. Right. So that would be renewable biogas, for example. This is a possible product. Other products that can be bioplastics. Some organisms have the capacity to store some material, and they store in the form of some components which have similar properties to plastics.
Okay.
And these are biodegradable plastics. And you can already imagine that that's interesting.
It is interesting because every time I'm at the grocery store, and I think I brought my canvas bag with me today, but everything on the conveyor belt is packed in plastic.
Exactly.
So what an impact that could have. Can you tell us a little bit about what industries are sort of watching this type of resources that we're able to get?
Yeah, the gas part of it is already very mature.
Okay.
The main problem with the utilization of the gas has to be done it has to do with the price of gas, right? So it becomes interesting for a wastewater treatment plant to use the gas or inject it in the grid only if the price of gas that they are getting is high.
Right.
Natural gas costs almost nothing, unfortunately. The fossil fuels are very, say, subsidized.
Yeah.
So it's hard to compete. But in some countries, the government counter-subsidizes biogas and the way that they pay a premium because you're producing a renewable resource. So there's some economics there, some industry. Bioplastics, there are startups, there's research working on, for example, other polymers that the organisms produce, that are high-value polymers. There is research in universities and in companies. They are trying to develop products, but it's not easy because also another problem is the price of plastic.
Yeah, of course.
Plastic costs nothing and it stays there forever. So it's how can you fight this?
Money makes the world go round.
Exactly. So it costs so low cost. So it needs to be it requires the help of governments and even the public ourselves when we decide not to use single-use plastics, right?
Yeah, absolutely. Where are we at? In terms of scalability or actually putting this into commercial use?
The bioplastic, I think there are already projects that are trying to be commercial. The problem is also the scale.
Yeah, exactly.
The scale of this industry based on fossil is enormous, right? So we know how big it is everywhere. So it takes entry into this is a little bit slow. But there are products you can find bags which are fully compostable. You need to look for the compostable ones because the biodegradable means they will disintegrate into little pieces of microplastic.
Absolutely.
Right?
Yeah.
So you need to actually look for
which gets
truly
into our bodies.
Yeah, exactly.
I mean, they're impacting our brain activity even at this stage.
So if they are coming from these biological processes, they will be biodegradable because they are part of biology. So they will be breaking down.
How excited
quickly.
are you about this?
Yeah, it's nice. It's actually nice areas of research. Other products are the production of chemicals of interest. For example, you can get fermentations to produce directly ethanol or other liquid fuels if you direct them correctly. These organisms can do that. And they can also create just intermediate chemicals that the industry can actually take as a commodity for other processes. So this whole thing works into this concept of circular economy, where everything is kind of going in a circle and nothing goes into landfills or the atmosphere.
Right.
So that idea is the ecosystem we're talking about.
I love it. Yeah, there's a company in Dubai, for those who aren't familiar with what circular economy is, that makes they make clothing out of plastic. So companies like the F1 track or I believe Warner Brothers World participate in this program where they put bins around their locations. All the plastic that goes in gets shipped over to them and they make the uniforms for them.
Nice.
So they're participating in a circular economy.
That's an example, yeah. This is an example.
What kind of impact would this have, say, on agriculture?
You mean something like
the products that or the resources? Are we looking at biomass?
Sure, yeah. Actually, in a place like the UAE where we don't have a lot of soil, in the sewage, the nutrients are there, right? Our human waste has the nutrients from the food that we take, right? So those nutrients, they don't disappear you can make them go away to the air, but you can also run the process biologically in a way that the nutrients stay in your biomass. So you do the biogas, but then you also get a nice product, which is fertilizer. You can use it as a fertilizer. So if you run the process properly, you can get something called biosolids at the end. You get your gas for heat or combustion, renewable energy. And then you can also have a fertilizer that you can apply directly to agriculture, provided it meets some requirements for, presence of some components, metals, and all like that. Okay. But that's normally, if all is fine, it can be used for soil generation, which will contain slow-release nutrients and slow-release carbon because everything is already stabilized through this biological process.
Further to the circular economy, this must contribute to the United Nations SDGs. Can you tell us a little bit about that?
Yeah, I mean the main contribution here is the water and sanitation, right? The sanitation is, I mean, the main reason why we do wastewater historically is public health, because you otherwise we have diseases spreading, right? So public health, wastewater and sanitation is one SDG for everyone. So biological systems can potentially be implemented everywhere, because there is always bacteria there. You can always run these processes. There are other sustainable production and consumption that's related to the circular economy. There's another SDG that is relevant as well. And obviously we contribute to the climate targets. If you are recovering resources and giving them a second life, if you keep things in a circle, things don't go in net in the atmosphere. So that's the idea with the carbon. You produce methane, renewable methane. You can just keep it in a closed loop of carbon.
Okay. This all sounds amazing, highly sustainable practice. Can you tell us a little bit about some of the challenges that might occur to implementing some of these processes?
So these technologies have advantages and disadvantages in the sense that they can be very low cost, because they basically work for free, right? These organisms, you feed them, they do the job, they grow a little bit, and then everybody's happy. Yeah. The problem is, if you use organisms that are, the natural organisms that are there, they will do a little bit whatever they want. So you don't have full control of some of the products. Some processes are very clear. You will get biogas. But if you're looking for a particular fuel, liquid fuel, you want to do, butanol because it's good for aviation fuel, then you're going to have a problem, because they might be wanting to do something else. So the challenges are in directing these organisms to do what you want. Okay. But if you do it, you could say, okay, then I can select the organism, the species that's what I want, right? But then you have to keep it in a clean environment, because if you pick one species of organism, how are you going to stop the other organisms to come over and take its food and do the other thing, right? So that's a bit of a challenge, whether you want to keep a clean environment, which is going to be expensive, like in the pharmaceutical industry.
Right, so we're looking at cost again.
You're looking at cost of capital, but then you have also the advantage of having not a very expensive reactor in which you can have every organism. The costs are much lower. Right. So if you can push that's where my research focuses on directing mixed microbial communities towards producing high-value products without going into the clean.
Okay, expensive. So you're trying to keep the cost down so that it's more attractive and will be adopted more widely.
That's the idea, and bring those technologies closer to market there.
Yeah. How close are you, do you think?
I mean, there are many processes. I like to work. One of the things that make me like this area of work is that we work in the interface of engineering, chemical engineering, and biology. And biology, we're still learning a lot about biology. Biology is the discipline of the 21st century. We learned almost all the physics in the last century. And now we're learning about biology, and we have incredible tools that we didn't have even 10 years ago. So you can edit the genes of living things. You can do incredible things with biology. So it's very exciting, because there's a lot of potential there to push.
Just needed the technology to catch up.
Yeah, I think so.
Yeah, it's interesting. I want to go back just for a second to when you were speaking about the soil opportunities within the UAE. Could this be something that contributes to the UAE's net zero by 2050?
Yeah, absolutely. If you have, in terms of the soil, the soil remediation.
Yeah, the soil
you're creating from renewable.
Anything really, but the soil comes to mind simply because it's a place.
It definitely contributes to the food security, because if you bring soil, then you're keeping the nutrients in the country. Yeah, exactly. You're importing them already with the food. So that nitrogen and nutrients, if you basically destroy them through the treatment, they go back to the air, right? Exactly. But if you keep them in the soil, then you're actually keeping them in the country, right, so you can grow food again on them. So that's one thing. I think it contributes to the net zero, because all these nutrients, they cost a lot of energy to make. So ammonia for fertilization uses a lot of energy, and energy comes with a carbon footprint. So you're actually contributing already if you recover ammonia. And then you have also, of course, the gas or the energy savings that you would have on all these biological processes. If you're producing methane, that means clean methane.
Yeah, and the UAE is very focused on food security and being self-reliant. And I would think that would be a big interest for them. So we've talked a little bit about how countries like the UAE can benefit from your research and what you're putting it into practice. Could wealthier communities benefit more from these resources in terms of, say, clean water, the products that can be developed, whereas poorer communities or third world countries may struggle because the technology isn't available for them.
Yeah, I mean, this happens like with every technology. At the end of the day, there might be different versions of it. So microbial wastewater treatment is very low cost. The difference becomes if you are aiming at building a very large-scale treatment facility in a city. That requires some investment, of course, like building a motorway,
right?
Obviously. But the alternative for wastewater treatment, which is also happening in many places, is that you don't transport all that water to a single place because it also becomes expensive to move all that water. You can actually treat decentralized, so you treat near the source.
Right.
So if you have a small community, they can have their own small treatment plant.
Okay.
And that can be a bit more low-tech. Low-tech, low-cost, low maintenance, and still be biological. For example, they can use wetlands, constructed wetlands, or they can use biotrickling filters, which they are basically circulating the water through a kind of a natural environment.
A lot of
bedrock,
them do that
and the
too.
bacteria grow there. The treatment actually happens through the bacteria that are naturally growing there. Okay. So it is actually, in essence, the same process, but it's just lower tech.
And it's really about education, isn't it?
Yeah, you require to have a bit of an understanding and how to run it, but it doesn't involve a very high cost of maintenance at that level. Another story, if you are trying to recover the biogas at large scale or produce valuable chemicals, then you're going to have to develop a bit of a higher tech process. But there are many examples already, even for centuries in rural China. They have these digesters that they use in the house. So they put their waste food underground, and that already is fermenting and producing the methane gas, and they use it for cooking in the kitchen directly. Amazing. This is happening, and probably there are millions of them around China.
It's amazing.
So that.
Interesting. So let's look at the bigger picture then. I'm going to ask a broad question. Do you think that microbial technologies can transform waste management?
I think they have already done that, to be honest. The advantage of microbial technologies is that we are aligning what we want to do with what they want to do, because if you're feeding them, they are happy, so they grow. So we are both happy, and then we're using basically free labor on that point of view. For environmental biotechnology, this is a way, and if we do it in a clever way, we can make them work towards more specific directions that generate more value for us. Right. And that's where our research also comes in, and that's also highlighting the importance of fundamental research as well, which brings in the true deep understanding of how things work, not only on the surface. Right. That's where the value of research comes in sometimes, not only applied in the last step of TRL. The biggest advancements in technology have come from really understanding the very fundamentals.
Yeah, exactly. Yeah. On a global scale, you still feel the same. Yeah,
absolutely. These are universal processes, so you can run them anywhere in the world. And they scale up very quickly because, bacteria can grow exponentially.
Right. Yes, they can.
Fast, so you can have these processes as many as you like.
Okay. And let's look forward a little bit into, say, a decade from now. Where do you see your field heading?
I think it will. There are some of these technologies already mature, so they will be probably. The costs will be slightly lower, and they will be implemented broadly. There will be a lot of optimization happening on the fine-tuning through maybe AI and advanced control, so you can gather much more data. There are a lot of molecular genetic tools that we have now we didn't have before. Those generate enormous quantities of data. So the learning from the analysis of those data might also come into place into something useful. And then for the high-value products, if we manage to understand this microbial ecosystems and microbial communities better, developing models in which we account for ecology, we account for chemistry, we account for everything we know, we can maybe direct them to these value products that we wanted without having to invest a lot of money.
So you'll develop a model where you can test it, and then you'll know.
The model is a tool for learning.
Yep.
And with the model and the learning, we then will design the reactors and the processes in a way that we can low cost, high value, let's say.
Sounds amazing. I look forward to packaging my groceries in something other than plastic one day.
There we go.
Is there anything you want to talk about today that I haven't asked?
Just to highlight again, maybe this idea of the value of fundamental research that is there. The problem with fundamental research is it takes longer time, but that's what really gets you the extra mile at sometimes. So I think it's real value in investing in not only applied but also fundamental. And I think here in KU we have good examples as well. There is investment in fundamental research, in learning about the science and learning about the mechanisms. And there is a lot of great research on investment on applied research and even entrepreneurship.
Would you say the fundamental research is a challenge these days for say, students who have grown up in a digital age and with AI and the way it's moving so quickly right now, it's a big part of their lives. And, you know, people being born right now, it's going to be, it's technology is everything. You know?
Yeah, we don't know how things are going to look like. I'm being honest with you on this. The challenge with fundamental risk is not a fast reward thing.
Yeah.
And you might not get any reward at all. But I mean, if we think about, we have iPhones in our pockets, the technology in these iPhones came from the physics we learned in the particle accelerator in Switzerland, and that required billions of dollars of investment to build a huge tunnel, and nobody knows what is that for.
Exactly.
So eventually we have what we have today. So this is a living example of it.
So I'm using my iPhone, but I know nothing about
how it
works or where that knowledge came from.
Yeah.
Interesting.
History of science, maybe. We can add that as an elective.
I think that's a great idea. Let's talk to the directors. Thank you so much for joining me today. I really appreciate it. It was a very interesting topic and conversation. Good luck with the research. We look forward to hearing how it progresses.
Thank you so much. Have a good time as well. Thanks.
Thank you for tuning in today. If you enjoyed this content or you would like to be a contributor, please visit our website at ku.ac.ae/KU Pulse.